Today's lecture is going to be about conditional statements. These are things that are actually pretty familiar to folks in the computer world. They're if-thens. Let me point out a difference. So this is this is section 2.2, conditionals. If you're doing programming, you've certainly run into this kind of thing before. You may have a snippet of code that looks something like this. If, and there'll be some condition in parentheses after the keyword if, and then usually you have braces, although in Python it's just I think it's a colon, and then you indent to show what happens if the condition is true. But like Java, for instance, looks more or less like this. If the condition, and then you're going to do something in here. And so if you were saying this to somebody, you'd say, well, if this condition is true, then we'll do something. So here are the words if and then. Of course, in the programming, often then gets avoided, although I've seen languages that include the then. But there's a difference between how an if-then is used in programming and how it's used in logic. So be aware of this. First of all, things like this would be written P arrow Q, where that guy's P, and the something there is Q. And in logic, though, what it means is this. If P is true, so far it's the same as what you're doing in the programming thing, but we're not going to say do Q, but rather Q is true as well. If P is true, then Q is true. So we're not saying that Q is some action we'll take, but rather it's some sentence, some statement that whose truth value will be true, provided P is true. Some names, some terminology for the bits of this. The first guy, P, is called a hypothesis. Fancy name. Hypo means under, thesis means thesis, like a piece of an argument. And so this means it underlies the argument. That's what it really means. Q is called the consequence, or also the conclusion. Actually, I think conclusion is the more common term. Well, actually, while we're at it, let me give you slightly less common synonyms for these. Hypothesis can also be called the antecedent. Ante means before, so the thing that comes before, and the Q is also called the consequent. Usually these pairs work that way. You wouldn't say hypothesis with consequent. It's a hypothesis and conclusion, antecedent and consequent. So there's an issue we've got to face about when is a P implies Q type sentence. When is one of these conditional sentences true? When should it be true? And I guess the standard take on this is that you should think instead about when is it for sure false. The notion is that we're going to give the speakers of a conditional sentence benefit of the doubt. I guess that's the way I'd like to phrase it. Benefit of the doubt. Meaning, we'll figure out where the P implies Q sentence for sure is false, and everywhere else it'll be true. Well, shall we do some examples? I'm just going to write capital T for true there because I'm running out of space. In the book, they have this sentence: if you show up for work Monday morning, then you'll get the job. So this is an example of this from the book. By the way, I'll mention that a lot of times the word then in these if-then sentences gets dropped, and you just have a comma there separating the if part from the then part. So if you show up Monday, you'll get the job. I hope you agree, just informally, that has the same logical content as if you show up Monday, then you'll get the job. So suppose the previous Friday, you've interviewed with some guy, and this is the statement he made to you. If you show up Monday, you'll get the job. When can you call this guy a liar? When can you say, that was a false statement that guy made to me? Well, it's if you show up bright and early on Monday, and he's already got somebody else working your job. Right? If you show up on Monday and you don't get the job, then he was lying. I think it's pretty straightforward to say, if you do show up Monday and he puts you to work, that his statement was truthful. But we get into weird territory when you think about what happens if you don't show up, or maybe you get there late. I mean, this guy could do what he wants. He could say, hey, I didn't say, stroll in at 11. I said, be here bright and early Monday morning, and then you get the job. So you show up at 11, and he's like, sorry, pal, you're out of luck. Would you call him a liar in that instance? I think not. You didn't do the if part that he said to do. I mean, okay, I left out the early Monday, but you get the idea. What about if you don't show up at all on Monday, but Tuesday you pop by bright and early and say, hey, can I still have the job? Maybe the guy really needs somebody to do this job, so he says, yeah, whatever, I guess, and lets you have the work. Can you call him a liar in that instance? You might call him soft, but I wouldn't call him a liar. So the benefit of the doubt is going to these cases where the if part doesn't hold. That's what's in the book. There's an example. I had the idea of doing 3 of these. I don't know if we need to do all 3 of them. Yeah, why not? Suppose you thought I was amenable to bribery and you came and approached me about this. I'm not, right? So this isn't going to work. But imagine that I made this statement. If you pay me $100, I will pass you for the course. And suppose, let's analyze the 4 possibilities. You could pay me, and then you could pass. Then my statement would have been truthful. Illegal probably, and at least unethical, but truthful. What if you pay me the money and I still fail you? I'm an unethical jerk in that case, right? And so you would be completely justified in saying that I had lied to you. But, what if you don't give me $100? Maybe you only give me $50. I could say, well, kid did pretty good on the tests, I'll pass him anyway. Or I could say, hey, didn't pay the full amount, fail. Right? The statement isn't a lie unless the if part happens and the then part doesn't. That's the example I want to know. My last example is from your home life, and you have to imagine yourself as a younger child for this one, because I think this largely doesn't apply to people in their late teens and early 20s. But a young kid, there's often a parental desire to get them to finish their food because, you bought the food and it's good for them and you want them to eat it, and they don't like certain things, whatever. So suppose mom says to you, if you finish your lima beans, or substitute whatever food you don't like. I don't care for lima beans, so you can have ice cream. I don't have enough room to write ice, well, maybe I'll just say ice cream. And we'll leave out the rest of the words. But it's, if you finish the lima beans, then you can have the ice cream. That's what I really want to get at. I think this example makes it very clear why you give the benefit of the doubt. Because if your mom is anything like my mom, and you called her a liar, you would be in serious trouble. Okay? So you better call her a liar only in the right circumstance. If you finish the lima beans, and she doesn't come across with ice cream, Mom, you did not tell me the truth. You said I was going to get ice cream if I ate those lima beans. She's been, but we're all out, and I don't want to go to the store. And, you know, those excuses. She didn't deliver. That's the one circumstance where you could get away with telling your mother that she had told a falsehood. But if you don't finish the lima beans, it's up to her. She could go soft and say, yeah, all right, you can have, you didn't finish most of them, so you could have some ice cream. Or she can hold firm and say, the lima beans are still on your plate, you're not getting dessert. And in either of those situations, you probably would not be wise to say your mother had said a false statement. Don't call mom a liar in situations where you really can't pin her down. That's the idea of benefit of the doubt. You only call an if then false if, what situation is it? P is true and Q is false. In that scenario, P implies Q, the whole thing is false. And everywhere else, it's true. Let's write up a truth table for this, this conditional connector. It's pretty easy because of this, this analysis we've just done. We only have to figure out where is the if then false, and everywhere else it'll be true. So how does that look? I guess we use P and Q for the inputs, and P implies Q then is the thing we're interested in. The pattern on a truth table is always, I always do it this way, the second variable alternates. True, false, and true, false. The first variable alternates but in groups of two, so two truths and then two falses. And then you might try to look through these and double check, have we actually covered all the possibilities, all the combinations that you could have for truths and falses? We have. True implies true. This is true. This is when you finish the lima beans and mom gives you the ice cream and you're happy. And the second line here is where we say mom lied to us. You finish the lima beans, she doesn't come across with ice cream. False. And these bottom two are where the benefit of the doubt thing comes in. We just say they're true. Now there's a fancy term for this benefit of the doubt idea, and it's the word is our vacuous truth. So we say these two are true vacuously. True for solid reasons, false for solid reasons, just true because the if part is not true, vacuously true. There's a couple of ways to phrase this connection between P implies Q. The straight up one is to say if P then Q, of course. One that is kind of popular is to read this arrow as the word implies. So it wouldn't be if anything, excuse me. You would say P and then the word implies where the arrow is. They mention in the book there's a slight quibble about this phrasing, which I frankly don't agree with, but it's fine. Apparently the word implies is used in a technical sense in philosophy to mean the truth of this one can be deduced from the truth of this one. That is, there's some string of logical connections you can make from P to Q, which isn't necessarily the case when you're talking about just P implies Q as arbitrary statements. They may not logically have anything to do with one another, but the world works this way. Just, if this one's true and that one's false, the thing will be false. I think you can probably forget about that quibble and just say, yeah, replacing the arrow with the word implies will, 99% of the time get the right meaning across. There's one last way, which is to sort of switch the order of the clauses here. Say if P second, that is, you would say Q, if P, which is weird phrasing, but it does work. I mean, I think you don't encounter this too much in American spoken English, but I believe in Britain it's maybe a somewhat more common thing. How would I say the ice cream and lima beans thing if we went it this way? It'd be ice cream if you finish your dessert. You can have ice cream if, I just said dessert, didn't I? You can have dessert if you finish the lima beans. Yeah, no, that's not an unreasonable phrasing for the same idea. Just so the key word if is what tells you that this one is the antecedent, and if sometimes you might want to just mention the consequent verse. Actually, that might be a good rhetorical thing, right? You lead off with the reward for a particular behavior you're trying to encourage. We got to mention something about order of operations, because we now have, let's see, what all things do we have now? And or, negation, and these conditionals. There's 4 things. And there's also parentheses, so there's really 5 things. If we're talking about logic, the PEMDAS rule is or the thing that we usually remember via the acronym PEMDAS is not what we're after, but parentheses still happen first. If you explicitly write in parentheses, it means do what's inside of them before anything else. Then negation is what happens next. The not sign. And or happen at the same level. So there's no precedence one over the other. And that means if you need it to be, do the ands first. You got to put some parentheses in to make that happen. And finally, conditionals, the arrow things, happen last. Okay. This, unlike PEMDAS, I don't think you can pronounce it. Maybe you can pronounce it pnaic. I don't know. It's pretty bad. But it's not that hard to remember. Okay, so we'll see an example of puzzling through what's the deal with the order of operations in a second. In fact, looking at my notes, right now we're going to see that deal. So the next topic to talk about is what are called logical equivalences. We've seen them already. But logical equivalences involving a conditional. And here's a nice example. P or Q implies R. So if either of P or Q is true, then R will be true. That's how I would read that. But that is logically equivalent to this. P implies Q and R. Sorry. P implies R and Q implies R. And this, while I said it, I was probably pronouncing it in such a way that you saw this as the conditional and the conditional with the and in between them. But if you read this according to these rules of precedence, the conditional happens last. So we should really do this, the R and Q. This really says P implies R and Q, which implies R. And that's not what's meant. I spaced it to sort of indicate what I meant, but to be really honest about it, I need parentheses around these conditionals, meaning evaluate the conditionals first and then and them together. So that's a logical equivalence. It's true. It may be a little surprising because we had an or between these guys, and now we have an and between the two separate things. So that looks weird, but well, let's check it out, because the one surefire way to check whether an equivalence like this is correct is write down a truth table. A truth table that has all possible mixtures of true and false for the variables. And this is another great spot for us right now because we've got 3 variables, so we get to make a truth table with 3 columns for the input variables. So it's going to take up the whole board. I did a raise. Okay. So we'll have P, Q, and R. You know what? I just realized I need more space on that side, so I'm going to pull this over to the left a bit more. P, Q, R over here. And then we'll need columns for our statements that we were going to compare. The first one was P or Q implies R. Notice because of the order of operation stuff, this or binds tighter than that conditional, so that really means P or Q implies R. The other guy, I do need the parentheses in, it's P implies R and Q implies R. All right, so let's start filling out this truth table. Remember the rightmost variable just alternates back and forth, true and false. Wait a second, do I really know this, that I have to have 8 rows in this table? Well, I do, but I mean, do you guys know this, that I need to have a table with 8 rows in it? There's 3 things, and you might think about, well, trues and falses, might as well think of them as binary, zeros and ones. How many binary triples are there? We've counted through them before. Actually, we counted through them on day 1. So that's pretty clear. There's 8 of them. And it comes out nicely from this pattern I've been showing you. This guy alternates directly, trues, false, true, false. The next one alternates in pairs, 2 trues, then 2 falses, then 2 trues, then 2 falses. And the last one alternates in 4 tuples. There's 4 T's in a row. One more. And 4 F's in a row. I'm having deja vu. I don't know if I pointed this out to folks before, but I like to put a dividing line down the middle of this table. Usually I don't bother dividing the rows, but when you've got something this big, it's easy to get off. Start writing a letter halfway between the rows. So this will help us stay aligned. Do you notice though that the top half of the table, right up here, I'm making a square around it that's sort of not necessary. That's exactly copied down below. So there's if you just restrict your attention to Q and R, that's a little bit of the 4x2 table that we used previously. And we've got another copy of that same pattern. TT, TF, FT, FF. TT, TF, FT, FF. Down in the bottom. The guy up front is true for the top half of the table and he's false for the bottom half of the table. So that's good. Okay, let's see if we can deduce the truth table of these, the truth values of these 2 things. I think I'm going to do a little piece of trickery that is kind of cheating, but it actually will help us in this, that we don't need to make extra columns. And the idea is this: right under a symbol, you can maybe write it in lightly. I'm going to use a blue marker so we see it, but you can write the value of just evaluating what's on either side of that. In other words, what's the result of just P or Q? Forgetting about the implies R for a second. That being an or statement, it's true whenever either side is true. So wow, it's going to be true in the entire top half of the table. In fact, where is it false? Where are P and Q both false? That's down here. So we'll have falses down here, and trues in these two, because let's see, well, yeah, the Q is true in both of those rows. Now, let's actually figure out what's supposed to go in this column, because what's supposed to go is the evaluation of this conditional. The stuff that's written in light implying R. Where is that going to be false? It's when one of these blue letters is true, but the column for R has a false in it. So here's a couple of places where it's false. False here and false here. We got true for the P or Q. We got false for R. You know what? How about any of these down here? True for that one, true for that one. Oh, here's another one, a third spot. False in R, but true with the blue. And well, everything else is going to be true, but let's work our way through it. These, anywhere there's F's, you've got the vacuous truth. And where blue is true and R is true, well, that's true for solid reasons. All right? So I often write this stuff in lightly in pencil or something and then erase it when I'm done, but you know, I guess let me just sort of squiggle it out. That was just scrap work, really not part of the final answer. So you want to leave what's visible being your final answer on this thing. We're going to have to do more scrap work on this other one because there's two conditionals that are going to need to be evaluated. So where is P implies R false, and where is it true? For conditionals, I often jump in and just look for the vacuous places. So wherever P is false, P implies R will be true. That means we're true in the entire bottom half of the table, right? Because that's where P is got all falses. Well, let's do the straight up thing, which is figure out where it's false. Where P is true and R is not. That's in row 2 and also in row 4. That's where the falses occur. Are these other two guys really true? True implies true and true implies true. Yeah, they really are. So we've got a TF, TF, and then TTTT pattern there. Let's try the same analysis for Q implies R, the other half of that thing. Here's a spot where it's false. We've got true implies false. True implies false. Here's another spot, that's row, I don't know what that is, 6. Anywhere else where Q is true and R is false? Looks like nah. Okay, so true everywhere else. Two vacuous truths there. Solid. Oh, look what we're getting in this. I didn't realize it. We're getting two copies of the table for just the regular if conditional. True, false, true, true. The top half of this thing is going to be true, false, true, true. I wish I'd been more clever and thought about that in advance. Of course, the part I put a box around, that's the usual pattern for two variables, and these are the two variables, Q and R. So we should have recognized we'd get the pattern true, false, true, true, both in the top and in the bottom half of the table. Oh, now we have to put all that together. We need to AND these blue things. So it's true there, false here, both sides that are false, true there, false. If either side is false, the AND will be false. There's true, there's false, and then a couple of trues. Now look at the two bits of black stuff. Oh, I guess I need to squiggle out my scrap paper work too, or try to erase it. They just match right on down the line. Trues, falses, trues, falses, trues, falses, trues, trues. They're identical. So that means that these two statements are indeed logically equivalent. In any scenario, they will give you the same result. Because we've literally listed every possible scenario for the truth values of P, Q, and R. There's a fairly common situation where we speak conditionals using the word or. The conditional can sometimes be, well, can always be expressed as a disjunction. When people do this using an or in a sentence to indicate a conditional idea, it's often in the guise of a threat. You say to somebody, do this, or, and you name a consequence of what not doing this will mean. So something like, how about we talk into the landlord and we say, fix the roof, or I won't pay rent. That's a pretty reasonable thing to say to somebody, right? If you got a hole in the roof or something, your tree fell on it and rain is coming into your house, you can say, look, I'm going to withhold paying the rent if you don't fix the roof. But I've phrased it as an or. Let's see if we can turn that or version of things with a threat in it into an if-then. How would you say it? As if something, then something else. I would say it in terms of negating this, I think. Let me see if you guys agree with me that this is the same idea. If you don't fix the roof, then I won't pay the rent. It was supposed to be a period. Wow. Now this feels just a little bit strange because there's negations in here. But if we want the thing here, this if-then, to be P implies Q, what should P be? This whole sentence, or this whole phrase, you don't fix the roof, that's P. And then, I won't pay the rent, that part would be Q. Right, so if I make those identifications, we've got P, arrow, Q. What's this guy in that sense? Well, P was don't fix the roof, so what is fix the roof? That's the negation of P. And Q was I won't pay the rent. Well, this thing ends with I won't pay the rent. So that's the same thing, the same Q. So here's our two sentences, just interpreted from standard language, from our understanding of the English here. But I think you'll find that these are indeed logically equivalent statements, or logically equivalent compound sentences. Let's check. How are we going to check? Yes, another truth table. So I think I'm going to leave that there so we'll see what it is we're trying to compare. And then this is nice because it's only two variables. We can make a little 4x2 input grid. So we'll have P and we'll have Q, and then we need columns for both of our friends there, not P, word with Q, and the conditional P implies Q. We filled that table out so many times by now, I think everybody's used to writing that pattern. Actually, we've just done the P implies Q thing before, so let's fill that out first. Remember, it's false in row 2. It's got vacuous truth because of the two F's down there in the bottom half of the table. So true here, and true here, and true up top. Because there's only one condition when P implies Q is false. That's where P is true, but Q isn't. Well, how about this negation of P ORed with Q? Remember that an OR sentence is true when either of the things on either side of it, or heck, both of them can also be true. So when is this OR sentence going to be true? Well, wait a minute. I think I harped on this last time. Let's turn our way of thinking around on that. An OR sentence is going to be false in exactly one location and true everywhere else if we're in this 2x4 setup. So which combination of the truth values for P and Q ends up having false on both sides of here? Because of the not, we want P to actually be true so that not P is false, and Q to be false because Q's unadorned. So it's right here. It's this row. Here we'll have not P is true, Q is false. I just said that wrong, didn't I? P is true, not P is false, Q is false. So not P and Q are both false, which is where the OR will be false. And it's true all the other spots. So again, look at these columns. They're identical. In any scenario of the potential truth values for P and Q, these computations give us the exact same result. That's an operational definition of equivalence. So I usually do something like this. Point at the columns and write the equivalent sign. I'm trying to adopt to the book's use of the equivalent sign like that, but it still bothers me. I really wanted to write that top bar a squiggly thing. Silly of me, I guess. Okay, well, that actually turns out to be quite a useful thing because we would like to know how to talk about the negation of an if-then. It turns out that for a lot of arguments, the first thing you have to do is suppose the negation of the thing you've got. That's how a method we're going to come into talking about a lot soon. Excuse me. It's called proof by contradiction. Works. The very first thing you do is need to find a negation. So that's going to become an important skill for us. What should the negation of P implies Q be? I mean, I can tell you what it looks like. Negation of P implies Q just needs to have exactly the opposite truth values that P implies Q does. So it would be false here, it would be true here, it would be false here, and false there. Just completely the opposite cases for what P implies Q is. That's what negation means. Can we figure out something that has this particular pattern? False, true, false, false. It's true in exactly one row. And statements are like that. Well, okay, which and statement should it be? Let me do a little bit of Boolean algebra for you. I'm looking for the negation of P implies Q. But that's equivalent because these two things are the same. That's the negation of not P ORed with Q. And by De Morgan's law, what is this? That's not P, and it with not Q. Double negation there means that's really P and not Q is low. So finally, this is P anded with negation of Q. And by the way, think about that sentence if you translate it into the lima beans / ice cream scenario. This is exactly what the kid is going to whine when their parent, made that promise and didn't follow through. They're going to say, "But I ate my lima beans and you didn't give me dessert." Right? So P and not Q actually makes good sense for what this should be, what the negation of P implies Q is, what this red column should be. And in fact, that's correct. That's the negation of P implies Q by Well, just a little train of logic there. We needed the double negation idea and De Morgan's law. So. And this idea that the conditional could be re-expressed as an or. So people generally are pretty bad at logic. Unless you've had some training and honed your mind to think carefully about the idea of conditionals, it's easy to get lost in the details. One particular error that people make all the time is confusing which way the arrow goes in a P implies Q or if P then Q kind of scenario. So let me give you an example. P is equal to gas in the tank. And Q is going to be the generator will start. Wouldn't most of you agree that this is valid? P implies Q. If there's gas in the tank, then the generator will start? Well, actually, that's not right. Think about this. Couldn't the generator fail to start because of some other reason? Maybe, I don't know. What else can go wrong with a generator? The spark plug is dirty. Maybe there's water got into the gas tank, so while there's gas in there, there's also water, and the water sinks, and that's what the generator would be trying to burn. So, in fact, this is not, the connection between that P and that Q is not P implies Q. In fact, what it is Q implies P. This one's wrong. See, if the generator actually starts, do you think that could be happening with no gas in the tank? Yeah, so Q implies P is, you hear the thing running, you know there must be gas in the tank. That's the correct logical connection between those two, not what it might seem at first. Well, this kind of error is so common that you have to have a name for it. This is called the converse error. The converse of a conditional is what you get if you just switch the order of the parts. Ooh, gotta really stretch to shrink that in there. The converse of the conditional P implies Q is Q implies P. And frankly, we mostly have the converse sitting around for us to tell people, you got that wrong. You mean the converse. Or you have made a converse error. Although that would only be something that philosophers or mathematicians might say to one another. I can't imagine anybody in like ordinary language telling their friend, oh, you've made a converse error, buddy. You might say, dude, you've got that switched around. It should be the other way. That might be fine, but you probably wouldn't use this terminology. But in this course, we're going to use this terminology. There's another error that people make. I'll just point it out to you by saying what it's called. It's called the inverse error. And this mostly, I think, stems from a kind of a wrong-headed idea of what it might mean to negate an if-then. Look at the pattern. I'm going to write here on the side of putting a not out in front of P implies Q. Doesn't it look like you should be able to distribute that not so you'd get not P implies not Q? Well, that's not what you can do, but that's what people sometimes think you can do. So we name that one too. The inverse of the conditional P implies Q is what I just said, not P implies not Q. Let me see if my writing can catch up with my mouth now. Not P implies not Q. Yeah. So converse, flip the order around. Inverse, put nots on the two parts of it, but leave the order fixed. So there's a great little thing that happens when you screw up both of these. So if you get the order wrong and you put the knots on the two parts of the thing, it turns out you actually get the original sentence again, or rather something that's logically equivalent to the original sentence. That's called the contrapositive. I don't know if I quite like the construction of the etymology of that word, but that's what everybody calls it. So let's follow this same construction here in parallel. The contrapositive of the conditional. Darn, I'm going to have to abbreviate conditional this time because I really ran it. Oh, it's because contrapositive is such a long word. P implies Q. Think about what it is if you both get the order wrong and put knots on the parts. We use the word is rather than an equivalent sign. Is not Q implies not P. Let me put this into the form of the gas and the generator running thing. Let's see, if we had the right order on things, the generator running implies there's gas in the tank. What does this thing say? It would be, if there's no gas in the tank, then the generator is not going to run. Contrapositive really has the same logical content. I'm going to try to convince you of these by writing a truth table, and then we'll see how the connections of all four of these statements. So we've got the original, the converse, the inverse, and the contrapositive, and they're all connected to one another. But first, let's do a truth table for this equivalence, that the contrapositive and the original conditional have the same logical content, they're equivalent to one another. This is really quick because we've done the P implies Q table a bunch of times already, so we can go fast. It's false in that row 2, it's true upstairs, and it's vacuously true down below. Okay. What about not Q implies not P? Well, I suppose what we want to do, since it is a conditional, we just want to locate that one spot where it's false. And I was just pointing to it, wasn't I? We want not Q to be true and not P to be false. Anyway, we want this whole thing to be true and this whole thing to be false. But that means we want P to be true so that not P ends up false, and Q to be false so that not P. We want to be in this row. That's where we get false. And everywhere else it's going to be true. Now, which ones we call vacuously true are different here. The vacuous truth happens in rows 1 and 3, where Q is true, so not Q is false. If the if part is false, we get vacuous truth here and here. So that's kind of intriguing, but depending on whether you're looking at the contrapositive or whether you're looking at the original guy, you have different ideas of vacuous. These two are vacuous for the contrapositive, and these two are vacuous for the original sentence. Seems like, with one or the other of these, everything is true only for vacuous reasons. Weird. Okay, so yeah, the contrapositive and the original conditional are equivalent to one another. That's what we're seeing, that these two columns come out equal. I'm going to model for you what I would want you to do, which is point at the two columns somehow and write equal or equivalent, or even just make that equivalent sign, but somehow indicate that, yeah, I've checked that those two columns are identical. All right, so let me make a table to lay out how these different statements are related to one another. What I'm going to do is put P implies Q in the upper left-hand corner of a big table. And if we jump across the vertical line here, if we move side to side, we'll take a converse. So these things on opposite sides of the table will be converses, which means this is going to be Q implies P, of course. Notice that this is a reflexive relationship, or a symmetric relationship. If Q implies P is thought of as the original guy, its converse is P implies Q. These two are converses, is another way to say it. You don't have to start with this one and end with that one. This way, vertically, flipping across this horizontal line, we're going to take inverses. So the inverse of P implies Q is not P implies not Q. And what goes in that bottom right corner? Well, that's where you've done both. You've taken the inverse and then take the converse of that, or take the converse and then take the inverse of that. You get the same thing either way. You'll get not Q implies not P. So let me label all of these. This is our original. This is its converse. And this is its inverse. And finally, this, I like to think of it as two wrongs make a right. If you do both the converse and the inverse mistakes, you end up with something that's the same logical content as the original, the contrapositive. So I already pointed out to you by doing a truth table that these two things are equal to each other. Let me sort of make a long, extended version of the equivalent sign there, triple bar equal sign there. But think about it this way. If I start with the converse, if I start with Q implies P, and make a converse and then an inverse, in other words, the same pair of errors, I've got something here. This inverse is actually the contrapositive of this Q implies P. So these two things are equal too. So it's a kind of a neat thing. The things diagonally across from one another in this table are equivalent. It's the original with the contrapositive, but also the converse of the original and the inverse of the original, they're equivalent to each other too. So the weirdness here is that you might think of the converse and the inverse as being separate errors that somebody might make. But in effect, they're the same error. I mean, no, they're not exactly the same error, but they cause the same logical problem because these two things being equivalent. Okay, I mentioned previously that a way to phrase P implies Q is to say Q if P. Remember that? Well, there's a way to phrase the converse. Q implies P. That's very similar, and it is Q only if P. Now, I don't want to really get into only ifs because I find them confusing myself, and it's rare that people use them. But what people do use is putting these two things together. So I'm going to change the order around, but you have a symbol that goes between two things where I said two things and I wrote the same thing, kind of weird. The symbol that goes between the two where you mean Q if P and only if P. Well, since I'm writing it as PQ, I'm going to say P if and only if Q. You've run into that phrase before, right? Didn't your mom say you can have ice cream if and only if you finish your lima beans? No, of course not. But she should have, because probably that's what she actually meant. The biconditional is a pretty strong thing. Yeah. Okay. So I just said the words. This is represented with a double-headed arrow. P implies Q, and it's called the biconditional. Because what it really is kind of a shorthand, or a shorthand for is two different conditionals, biconditional. So what this literally means is P implies Q and Q implies P. Little practice about order of operations. Do you think I need some parentheses in this, what I've just written? I hope you do, because and would happen before the conditionals. So this would simplify to Q and Q, which is just Q. And so we'd have P implies Q implies P. Maybe that would be okay, but we really want it to be these two things. This conditional and this other conditional. That's what we're trying to get at. I'll finally mention there is a really common abbreviation for if and only if, because it's such a long phrase. People will write P, I, F, F, Q. Or at least math people will do that. I don't know if computer people do that or not, but probably should. I mean, shorthand, a lot less work than writing all that out. But the main issue with it is your spell checker will not know this. I'm always having to add the word IFF to the dictionary on my spell checking software because they think you've just made a typo. Yeah. All right. One last little thing to handle in this section, and it's just, well, it's a bit of phrasing that gets used only occasionally, but I just want you to sort of be forewarned that you'll know what's going on if you run into this phrasing. The phrases are necessary and sufficient. So let me watch the. If you have two sentences, R and S, and the conditional that goes between them like that, you can actually say this in multiple ways, but using the word sufficient, it is R is sufficient for S. I just crowd that at the end. R is sufficient for S. Meaning, if R is true, that's enough. That's what sufficient means. It's enough. You'll know that S is true. An example of this might be hearing the engine running. Could be R. And S would be knowing there's gas in the tank. Would you agree with me that R is sufficient for S? If you hear the generator running, you do indeed know that there's gas in the tank. It's enough. It suffices. Okay, the other term that's used is necessary. Let me do this in sort of the reverse order. Let's write the phrase first. We'll say R is necessary for S. Because what this means is actually the inverse. It's not R implies not S. So in the example from the generator and the gas and all that stuff, what's necessary for the engine to be running? Well, fuel in the tank is necessary. It's not sufficient. So if I do this correctly, then R could be fuel in the tank. I hope you'll be okay with me just saying there's fuel when you get the idea of it. And S could be the engine runs, the gen runs. Does it sound in natural language okay if I say it's necessary for there to be fuel to get the generator to run? I think that sounds right. Let's look at it in terms of not R implies not S. What it's saying is, if there's no fuel, then it's not going to run. And that makes sense too, doesn't it? But this guy is equivalent to, well, that's just the inverse of R implies S, so it's the same as the converse of R implies S. In other words, it's the same as S implies R. And mostly, I'm going through this because there's another phrase that gets used, and this one's more common, where you put the two of these things together. You say R is a necessary and sufficient condition for S. So what does that mean? Let's leave that on the screen and that on the screen. If I say R is necessary and sufficient, that's the phrase I want to analyze, because we do in fact hear this one fairly often, especially in the situation we're in now, where we're studying logic in a formal way. If you've got a necessary and sufficient condition for S, it means both R implies S, that's sufficient, and not R implies not S, that's necessary. The two of them together are R implies S and this, but that's the same as that. So what this really means is R implies S and S implies R. And that, finally, that's equivalent to the biconditional. Well, R if and only if S. So when you hear the connection R if and only if S, you may sometimes hear it phrased as R is both necessary and sufficient for S. All right, that brings us to the end of section 2.2. Kind of a lot in there, but it's cool stuff, I think. I mean, you know, it's really getting handy with dealing with these conditional ideas is going to make you a better thinker. It really is cool. It'll strengthen your ability to reason critically about lots of things. So anyway, that's that. This is being posted on Saturday of the Labor Day weekend. I hope that everybody will get a chance to view it before our class on Tuesday. There's plenty of time before class, so I'll send out an email with a reminder about that. And anyway, I hope you're enjoying your holiday weekend, and I'll see you on Tuesday.